prove that the square root of 3 is irrational. A lot of members have been asking me, is the square root of 3 rational or irrational? And we want to prove that the square root of 3 is irrational. And we will use a form of proof that is proof by contradiction. And by contradiction, we will say, let square root of 3, the square root of 3 to be rational. And if the square root of 3 is rational, then it means it can be represented in a fraction. That's a over b, where a, it means that square root of 3 equals to, can be represented as a over b, where a and b are integers. They are integers and they are members of integers, and b is not equal to 0. That's if square root of 3 is rational by assumption. The first assumption we make is that it can be represented as a fraction. It is rational. The first assumption. The second assumption, assume it is irreducible. Assume that the square root of 3 is irreducible. And what do you mean by saying it is irreducible? By saying it is irreducible, it means it is of co-prime numbers. Or it exists in its simplified form, or the only common factor, or the GCD between A of A and B is just 1. And if this one contradicts, then square root of 3 will be irrational. Now let us claim that it is rational and it can be written in a fraction form, that is in rationality, and it is reducible. Then let's find the solution. The square root of 3 equals to a over b, where by we square this, so that we get rid of the square root. So we have 3 equals to a over b, a squared over b squared. And we can cross multiply so that we have a squared. We cross multiply 1 and a squared, then 3 by b squared. That's a squared equals to 3b squared. Now, by the Euclidean rule, or theorem, a squared if 3 is a factor of a, then it means that 3 is a factor of 3a squared. It means that 3 is also a factor. This ought to be a factor of a, because by Euclidean rule, if a prime number 3 divides a and again divides a product of a times a, it means that the 3 divides a also. Now we have found that indeed a is a factor. which is a contradiction, of course. And from equation 1, we say that a squared, members, equals to 3b squared. And let us assume that a squared equals to, from equation 1, let us assume that a squared equals to 3 multiplied by equals to 3 multiplied by an integer, let's say k squared equals to 3b squared. This one and this one. So we can go further and say this one equals to 9k squared, which equals to 3b squared. If we divide by 3, then we have 3k squared equals to b squared. And again, it means that 3 is a factor of b squared, because if we multiply 3 by an integer k, we will find k squared, an integer k squared, then we will find b squared, which thus also says by Euclidean rule that 3 is a factor of b, which is a contradiction, because square root of 3 has more than one common factor or divisor, that is more apart from 1, there is 3 is a factor of a, and 3 again from part 2 is a factor of b. This means that it is reducible. Which of course contradicts our claim that square root of 3 is reducible, meaning that square root of 3 equals to a over b is irrational, meaning that it cannot be represented as a over b, that is in form of integers. Therefore, please note just a recap. Please note that in this equation 1, a squared equals to 3b squared means that 3 is a factor, because 3 is a factor of a squared, because 3 multiplied by an integer b squared will give us a squared. Please note just a recap. Please note that in this equation 1, a squared equals to 3b squared means that 3 is a factor, because 3 is a factor of a squared, because 3 multiplied by an integer b squared will give us a squared.